Look up at the night sky. Really look at it. Those distant pinpricks of light aren't just stars. They're messages from the cosmos, written in a language of shifting colors. For over a century, astronomers have decoded these signals, believing they tell a simple story. The universe is expanding, stretching galaxies away from us in a grand celestial dance. But what if that's only half the truth? What if redshift, the very phenomenon we use to measure cosmic distances, is hiding secrets that could rewrite everything we know about space, time, and the fabric of reality itself? This isn't just about tweaking a textbook definition. We're standing at the edge of a cosmic mystery so profound, it challenges the foundations of modern physics. Think about it. Light traveling billions of years to reach us doesn't just arrive tired and stretched. It carries clues to forces we're only beginning to imagine. Some of these clues hint at exotic physics like light losing energy as it battles unseen dimensions. Others suggest we've misread the universe's expansion entirely, mistaking something far stranger for a simple balloon inflating. And then there are the wildcard theories. Could redshift be evidence of a universe much older than we thought, or even a shadow of another cosmos brushing against ours? Today, we're not just exploring one explanation but 36, each a doorway to a radically different understanding of reality. From forgotten ideas buried in old journals to bold new hypotheses cracking open modern astrophysics, this journey will take you past the edge of known science. You'll meet thinkers who dared to question the mainstream, discoveries that don't fit the standard model, and possibilities so thrilling, they blur the line between science and speculation. So ready your curiosity. By the time we're done, that night sky won't look the same because redshift isn't just a measurement. It's a riddle the universe has been whispering to us all along. The story of redshift begins not with certainty, but with a puzzle. In the early 1900s, astronomers noticed something odd about the light from distant spiral nebulae, what we now know as galaxies. The spectral lines, those chemical fingerprints etched into starlight, weren't where they should be. Instead, they slid toward the red end of the spectrum, as if the light itself was stretching on its journey across the cosmos. When Edwin Hubble linked this redshift to the distances of galaxies in 1929, the conclusion seemed inescapable. The universe was expanding, fleeing outward in all directions like dots on an inflating balloon. But here's what rarely gets mentioned. Hubble himself hesitated to call this proof of cosmic expansion. In his papers, he carefully avoided endorsing any single explanation, leaving the door wide open for other interpretations. And there were plenty. Some scientists proposed that light might simply grow tired over vast distances, losing energy like a marathon runner slowing over miles. Others wondered if the very fabric of space-time could be changing subtly over eons, altering how light travels. Yet these ideas faded as the Big Bang theory gained momentum, fueled by the discovery of cosmic microwave background radiation in the 1960s. The expanding universe became the dominant narrative, so convincing that questioning it seemed almost heretical. What's fascinating is how much we've overlooked in that rush to consensus. Forgotten notebooks and lesser-known papers reveal a chorus of dissenting voices. Take Fritz Zwicky, the brilliant yet prickly astronomer who argued as early as 1929 that photons might interact with interstellar dust or other matter, gradually reddening without any expansion at all. Or consider the work of Paul Dirac, who speculated that fundamental constants like the speed of light could change over time, warping our measurements in ways we're only beginning to grasp. These weren't fringe ideas, they were serious challenges from some of the brightest minds of their era, sidelined not by evidence, but by the sheer gravitational pull of a compelling story. So why does this history matter today? Because every assumption we've built atop Hubble's observations, dark energy, the universe's age, even its ultimate fate, rests on the belief that redshift has just one true meaning. But science thrives on questioning its own foundations. As we peel back the layers of cosmic history, those early doubts resurface with new urgency, whispering that our universe might be stranger, richer, and far more mysterious than we've dared to imagine. We've all heard the classic analogy, a train whistle dropping in pitch as it speeds away, the sound waves stretching out just like light from a receding galaxy. It's a tidy explanation, one that's been repeated in classrooms for decades, but the cosmos plays by far stranger rules than a locomotive. The Doppler effect works perfectly for objects moving through space, like that train or a passing ambulance. Yet when we talk about galaxies drifting apart, we're not just dealing with motion, we're dealing with the very fabric of reality stretching beneath them. Picture this: two ants on a rubber sheet. If the sheet expands, the ants move apart even if they're not walking. That's cosmic expansion. The redshift we measure isn't from galaxies racing away through static space. It's from space itself growing, elongating light waves as they travel across an ever-widening gulf. This distinction flips the script entirely. A Doppler shift implies motion against a fixed backdrop, but cosmological redshift, it's the backdrop that's doing the moving. Now here's where things get really interesting. If space-time's stretch can mimic a Doppler shift, what else could? Imagine light passing through regions of space where the laws of physics subtly change, perhaps where dark energies grip titans, or where unknown particles sap photons of energy over eons. Some theories suggest redshift might not even require expansion at all. What if light simply ages, reddening like an old photograph as it crosses unimaginable distances? Or what if our measurements are skewed by vast cosmic structures bending light in ways we haven't accounted for? The moment we question the Doppler assumption, a universe of possibilities unfolds. Alternative explanations don't just tweak the edges of cosmology, they rearrange the puzzle entirely. And that's why this misconception matters. It's not just about correcting a textbook illustration. It's about recognizing that the universe often hides its deepest truths behind deceptively simple appearances. The next time you hear that train whistle analogy, remember, the cosmos rarely settles for being that predictable. Fritz Zwicky's tired light hypothesis was the cosmic equivalent of suggesting the emperor might not be wearing clothes. While everyone else marveled at the expanding universe, he asked a deceptively simple question: what if light doesn't need stretching space to turn red? What if, after traveling billions of years through the void, photons simply run out of steam? Imagine a marathon runner crossing a desert, not because the finish line is moving, but because each step saps their energy. That's the essence of tired light: no expansion, no stretching fabric of space, just light gradually losing its vigor like a fading ember. At first glance, the idea seems almost quaint, a relic from cosmology's early days. But peel back the layers and you'll find modern physicists giving it fresh life. One compelling twist comes from quantum gravity, where space-time isn't smooth but foamy at microscopic scales. Photons traveling through this quantum froth might scatter subtly like a hiker slogging through sand. Each tiny interaction steals a bit of energy, shifting light toward the red over cosmic distances. Then there's the plasma hypothesis. Our universe isn't truly empty. It's filled with ionized gas remnants of ancient supernova, charged particles drifting between galaxies. If photons interact with this plasma, even weakly, they could transfer energy to it, reddening imperceptibly over eons. critics pounce on tired light for a key reason. It struggles to explain the cosmic microwave background's precise blackbody spectrum, a smoking gun for the Big Bang. Yet even here, surprises lurk. Some theorists propose that tired light could coexist with an expanding universe, acting as a secondary effect that tweaks our measurements. Others point to anomalies in supernova brightness that don't quite fit standard expansion models. Could tired light help fill those gaps? The real lesson isn't whether Zwicky was right or wrong. It's that science advances when we question what seems settled. Tired light forces us to ask, how much of redshift is expansion, and how much might be something else entirely? In a cosmos full of dark matter, dark energy, and other mysteries, dismissing alternatives outright might be the riskiest assumption of all. Einstein's general relativity gave us a startling prediction. Light climbing out of a gravitational well doesn't just slow down, it loses energy, stretching its wavelength toward the red. We've seen this in action near black holes and dense stars, where gravity's grip is unmistakable. But here's the twist. What if the entire universe is playing this game on a grander scale? Imagine light traveling past galaxies, clusters, and dark matter halos for billions of years. Each encounter, each tiny gravitational tug, could add up to a redshift so significant, we've mistaken it for cosmic expansion. This isn't just theoretical sleight of hand. Picture a beam of light leaving a distant quasar. On its journey to us, it doesn't fly through empty space, it weaves through a cosmic web of matter, passing near galaxies draped in invisible dark matter. Every time it skirts one of these massive structures, gravity steals a fraction of its energy, like a marathon runner handing off small weights to spectators along the route. Over billions of light years, these microshifts could compound into the substantial redshifts we observe. No expanding universe required, just the quiet, cumulative work of gravity's invisible hand. Critics argue that for this to explain Hubble's observations, the universe would need far more matter than we've detected enough to make gravity's influence outweigh expansion entirely. But dark matter, that enigmatic substance outweighing visible matter 5 to 1, might hold the key. If dark matter is clumpier than we think, or if it interacts with light in ways we haven't yet measured, gravitational redshift could sneak into the spotlight. Some models even suggest that certain configurations of cosmic voids and filaments might amplify the effect, mimicking expansion without any actual stretching of space. The beauty of this idea lies in its audacity. It takes a phenomenon we know exists, gravitational redshift, and scales it up to cosmic proportions, offering a static universe as a legitimate alternative. While it doesn't yet dethrone the Big Bang model, it forces us to ask, how much of what we see is truly expansion, and how much is the universe's hidden architecture subtly bending the rules? In a cosmos where dark matter still eludes our understanding, dismissing this possibility outright might mean missing a clue written in gravity's faintest whisper. Plasma cosmology throws a cosmic curveball at everything we think we know about redshift. Forget dark energy stretching the universe apart. This theory suggests the answer lies in the electrified soup of particles filling space. Picture the cosmos not as an empty void dotted with galaxies, but as a vast ocean of ionized gas, where electromagnetic forces choreograph the dance of light itself. At the heart of this radical idea stands Hans Alfvén, a Nobel Prize-winning physicist who dared to challenge the gravitational dogma of modern cosmology. His work revealed something astonishing. Plasma, that fourth state of matter we often ignore, might hold the keys to redshift's deepest secrets. The logic is deceptively simple. Space isn't truly empty. Between galaxies, there's a thin haze of charged particles, remnants of ancient stellar explosions. cosmic rays and primordial hydrogen stripped of its electrons. When light travels through this plasma, it doesn't glide uninterrupted. Instead, it interacts with the sea of ions and electrons, subtly losing energy like a radio signal fading through static. Over billions of light years, these tiny interactions could redshift starlight without any need for cosmic expansion. It's as if the universe isn't stretching, it's just foggy, and we've been misreading the haze as motion. Recent supercomputer simulations add fuel to this provocative idea. Researchers modeling plasma behavior found that large-scale waves called Alfvén waves could ripple through the intergalactic medium, creating regions of varying density. Light passing through these undulating waves would scatter and shift, mimicking the patterns we attribute to an expanding universe. Even more striking, some models reproduce the cosmic microwave background's temperature variations without invoking a Big Bang, suggesting plasma physics might offer an entirely self-contained explanation for multiple cosmological puzzles. Skeptics rightly point out hurdles. Plasma cosmology struggles to explain why distant supernovae appear dimmer than expected, a phenomenon usually credited to dark energy's accelerating push. Yet proponents counter that electromagnetic effects could alter light's journey in ways we're only beginning to model. And let's not forget plasma makes up 99% of the visible universe. Dismissing its potential influence on redshift might be like studying ocean currents while ignoring the water. What makes this theory so compelling isn't just its defiance of mainstream ideas, but its reminder that the universe rarely surrenders its secrets to a single perspective. Whether plasma cosmology ultimately holds up or not, it forces us to confront an electrifying possibility. The redshift we've used to map the cosmos might be telling a far richer story than expansion alone can explain. The speed of light, that universal constant etched into physics textbooks as 300,000 kilometers per second, might not be so constant after all. This audacious idea turns cosmology on its head, suggesting that light's velocity could have slowed over cosmic time, subtly warping our measurements of redshift. Imagine if the universe's ruler wasn't fixed but shrinking, making distant galaxies appear farther away than they truly are. That's the radical proposition behind variable speed of light theories, where the very foundation of relativity becomes a moving target. At first glance, the concept seems to defy logic. Einstein's special relativity hinges on light's unwavering speed, weaving it into the fabric of space-time itself. But dig deeper and cracks emerge. Some early universe observations, like the precise temperature fluctuations in the cosmic microwave background, hint at physics beyond our standard models. If light traveled faster in the ancient cosmos, it could explain why distant regions appear so uniformly smooth, solving what's known as the horizon problem without invoking cosmic inflation. Picture two mountain peaks separated by a valley. If light moved infinitely fast, they'd instantly share temperature. But if light's speed was merely higher in the past, those peaks could equilibrate naturally, no inflation required. The implications ripple outward. If light slows over eons, then redshift becomes a hybrid signal, part cosmic expansion, part decaying speedometer. This could explain anomalies like quasars with extreme redshift seemingly embedded in lower redshift galaxies, a puzzle that currently forces astronomers to invoke improbable alignments. More startlingly, it opens the door to theories where fundamental constants evolve. Paul Dirac first floated this notion in the 1930s, suggesting gravity might weaken over time. Modern extensions propose an intricate dance between light speed, the strength of electromagnetic forces, and even the quantum vacuum's energy. Critics pounce on a key objection. Altering light speed risks unraveling well-tested physics, from nuclear reaction rates in stars to the precision of GPS satellites. Yet proponents counter that only light speed in the early universe need differ, leaving present-day physics intact. Some models even preserve relativity's core by allowing all speeds, not just light's, to shift in concert, like a cosmic clock gradually ticking slower. What makes this idea so electrifying isn't just its challenge to textbook physics, but its reminder that science progresses by questioning its most sacred assumptions. The next time you see a star's redshift, consider we might be measuring not just space's stretch, but time's quiet erosion of the universe's oldest constants. Quantum foam, the very term sounds like science fiction, but this bizarre feature of our universe might hold the key to one of cosmology's greatest puzzles. Picture so-called empty space not as a void, but as a seething ocean of virtual particles popping in and out of existence in fractions of a second. These fleeting disturbances, predicted by quantum field theory, are more than mathematical oddities. They could be subtly altering the light traveling through them, stretching photons over cosmic distances like invisible hands tugging at a cosmic rubber band. Here's how it might work. When a photon journeys across the universe, it doesn't glide through nothingness. It navigates this quantum foam, where particle-antiparticle pairs constantly blink into being only to annihilate moments later. Every time a photon encounters one of these virtual particles, it could exchange a tiny amount of energy. Think of a hiker brushing against leaves on a forest trail, each touch slowing them down imperceptibly. Over billions of light years, those micro-interactions might add up to the redshift we observe, no cosmic expansion required. It's as if the vacuum itself has a kind of friction, one we've overlooked because its effects are vanishingly small on human scales. The math behind this is both elegant and mind-bending. Quantum electrodynamics predicts that virtual particles polarize the vacuum, creating regions of fluctuating electric fields. Photons passing through these regions scatter slightly, a phenomenon known as Delbruck scattering. While normally negligible over intergalactic distances, this scattering could gradually sap energy from light, redshifting it without any need for the universe to stretch. Some theorists have even calculated that the effect could mimic Hubble's law, the very relationship we use to measure cosmic expansion, but there's a catch. For quantum vacuum interactions to fully explain redshift, the energy loss would need to be finely tuned. Too strong and distant starlight would blur or distort in ways we don't observe. Too weak and the effect vanishes into noise. Yet intriguingly, anomalies in high-energy gamma rays, like those from distant blazars, show unexpected absorption patterns that could hint at vacuum interactions at play. Even more provocative, certain interpretations of dark energy suggest the quantum vacuum isn't static but evolves over time, potentially leaving its fingerprint on redshift measurements. What makes this idea so compelling isn't just its audacity, but its reminder that the universe's emptiest spaces might be its most fertile ground for discovery. If quantum foam leaves even a faint trace on starlight, it means every photon reaching our telescopes carries not just the story of distant galaxies, but the hidden turbulence of the void itself, a turbulence we're only beginning to decode. Cosmic inflation burst onto the scene in the 1980s as a dazzling solution to some of the universe's deepest mysteries. Why space appears so uniform in all directions, why no magnetic monopoles have been found, and how tiny quantum fluctuations could seed all the galaxies we see today. The theory proposed that a fraction of a second after the Big Bang, the universe underwent an exponential growth spurt, expanding faster than light itself. But here's the twist no one saw coming. That primordial stretch might still be echoing through our measurements of cosmic redshift today. Think of inflation like a cosmic magnifying glass. Quantum fluctuations smaller than an atom were blown up to galactic scales during that explosive expansion, eventually collapsing under gravity to form stars, galaxies, and the vast cosmic web. But inflation didn't just magnify space, it imprinted a specific pattern on those fluctuations, a signature that should still be detectable in how galaxies cluster across the sky. When astronomers study redshift surveys mapping millions of galaxies, they're not just seeing expansion, they might be glimpsing the frozen ripples of inflation itself. The smoking gun, baryon acoustic oscillations, those subtle, ring-like patterns in galaxy distributions that act as cosmic yardsticks. These oscillations are essentially sound waves frozen in time from when the universe was a seething plasma, and their precise spacing matches inflation's predictions eerily well. But there's a catch. Some measurements of these oscillations show slight deviations from expectations, particularly in how redshift correlates with distance at extreme scales. Could these anomalies be hints that inflation's stretch didn't switch off cleanly, leaving behind subtle gradients in space-time that still affect light today? Even more provocative is the idea that inflation didn't end everywhere at once. Some regions of space might have continued inflating while others stabilized, creating a patchwork universe where redshift measurements vary depending on which cosmic neighborhood you're observing. This eternal inflation scenario suggests our visible universe might be one bubble among countless others, each with its own physics and its own redshift rules. Critics argue that inflation's flexibility makes it nearly impossible to falsify, adjusting to explain any new observation, yet its persistence isn't just stubbornness. The theory's predictions about cosmic microwave background polarization, the swirling patterns in the universe's first light, have held up to astonishing precision. The real question isn't whether inflation happened, but whether we've underestimated how deeply its fingerprints linger in the light we see now. Every redshift measurement might carry not just the story of galaxies moving apart, but the ghostly afterimage of spacetime's most violent and transformative moment. String theory paints a cosmos far stranger than we see, a reality where our universe might be just one sheet fluttering in a higher dimensional breeze. These theoretical sheets, called branes, could stretch across hidden dimensions we can't perceive. Now imagine this: what if cosmic redshift isn't from galaxies moving away at all, but from our entire brane universe vibrating or drifting through unseen dimensions? Picture a guitar string vibrating. Its pitch changes as it moves. If our universe is like that string, its oscillations could stretch light waves, mimicking expansion without any actual stretching of space. The math behind this is dizzying. In some brane world models, collisions between branes could trigger events resembling the Big Bang, while their relative motions might imprint patterns on light crossing our brane. Light traveling parallel to a brane's vibration would redshift subtly, like a runner struggling against a shaking treadmill. Even more intriguing, if our brane isn't perfectly flat but warped by gravity from neighboring branes, light could take detours through extra dimensions, emerging with its energy altered. These effects wouldn't just tweak redshift, they'd rewrite how we map cosmic distances entirely. Evidence for this remains elusive, but tantalizing clues linger. Certain anomalies in the cosmic microwave background, those faint temperature variations, show patterns some theorists argue align better with brane interactions than standard inflation. Then there's the mystery of ultra-high-energy cosmic rays, particles arriving with energies so extreme they should have been absorbed by the cosmic microwave background. Unless perhaps they took shortcuts through curled-up dimensions, bypassing the usual energy loss. If branes are real, their hidden dances might be hiding in plain sight within the redshift data we've collected for decades. Skeptics rightly point out that without direct proof of extra dimensions, brane worlds remain speculative. Yet their very possibility underscores a profound truth. The universe's greatest trick might be making us mistake its shadow for its substance. Redshift could be more than a measurement. It might be a message from dimensions just beyond our grasp, waiting to be decoded. Dark matter has always played the role of the universe's invisible architect, its gravity sculpting galaxies into spirals, bending light into cosmic mirages, and holding clusters together like hidden glue. But what if its influence runs even deeper? What if dark matter isn't just bending light's path but subtly altering its very essence? This isn't science fiction. Cutting-edge models suggest dark matter could be quietly tweaking the wavelength of photons as they journey across the cosmos, creating redshift without a single inch of space stretching. Imagine a beam of starlight traveling through a halo of dark matter enveloping a galaxy. We've long assumed these mysterious particles interact with light solely through gravity, warping space-time like a heavy blanket. But some theories propose dark matter might have a whisper of non-gravitational influence, perhaps through ultra-weak forces or fleeting quantum interactions. Each time a photon brushes against a dark matter particle, it could exchange a sliver of energy, like a runner passing through a mist that slowly soaks their clothes. Over millions of light-years, these microshifts could accumulate into the redshift we observe, mimicking cosmic expansion while the universe stands perfectly still. The math behind this is as elegant as it is radical. Certain action like dark matter candidates hypothetical particles lighter than electrons could create oscillating fields as they ripple through space. Photons traveling through these fields might undergo a subtle energy drain, akin to sound waves losing pitch as they pass through fog. Even more intriguing, this effect could vary based on the photon's wavelength, potentially explaining anomalies in quasar spectra that standard cosmology struggles with. Some simulations show that if just 1 in a trillion dark matter interactions imparts energy to light, it could skew our cosmic distance ladder entirely. Critics argue that for dark matter to explain redshift fully, its distribution would need to be far clumpier than current observations suggest. Yet here's the twist: we've only mapped dark matter's large-scale structure. At smaller scales around individual galaxies or cosmic filaments, its true texture might resemble froth rather than smooth halos, with dense pockets capable of magnifying redshift effects. Recent observations of oddly correlated galaxy motions and unexpected light dispersion from distant supernova could be early hints of this hidden granularity. The most tantalizing possibility: dark matter's redshift mechanism might not replace cosmic expansion but augment it, adding a layer of complexity to our measurements. If true, it means the universe's acceleration could be slower than we think, or that dark energy's dominance is an illusion born from misreading light's journey. Either way, the lesson is clear. In a cosmos where 95% of reality is invisible, even our most trusted cosmic signals might be carrying messages we're only beginning to decipher. Einstein's theory of general relativity revealed something mind-bending. Time doesn't tick at the same rate everywhere in the universe. Near massive objects like galaxies or black holes, gravity's grip slows time itself, like a clock submerged in molasses. Now here's the cosmic twist. If time runs slower deep inside a galaxy's gravitational well, light struggling to escape would lose energy, stretching its wavelength toward the red. This isn't just theoretical. We've measured it on Earth with atomic clocks at different altitudes. But scale this up to galaxies and suddenly, redshift takes on a startling new meaning. Picture a photon born in the heart of a colossal galaxy cluster, where gravity warps space-time into a profound valley. As the photon climbs out, it's not just battling gravity's pull, it's racing against a distorted flow of time. From our perspective, that photon appears to have aged slower during its escape, like a traveler returning from a planet where years pass like days. The result? Its waves stretch, reddening as if the galaxy were fleeing from us, even if it's perfectly still. This gravitational time dilation could mimic cosmic expansion so precisely that we've been measuring it for decades without realizing its true source. The numbers are staggering. For a galaxy weighing a quadrillion suns, time at its core could lag behind intergalactic space by 1 part in 10,000. That might seem negligible, but multiply it across billions of years of cosmic history, and the accumulated redshift could rival what we attribute to the universe's expansion. Some calculations suggest that if galaxies are denser or more massive than we've estimated, perhaps due to unseen dark matter halos, their combined time warping effects might account for a significant fraction of Hubble's law. Yet there's a catch. For this to work universally, we'd need galaxies distributed in a very specific way, their masses and distances finely tuned to produce the smooth redshift gradient we observe. Critics argue that galaxy clusters aren't uniform enough to pull off this cosmic sleight of hand. But what if we're missing part of the picture? Modified gravity theories propose that dark matter's effects might amplify time dilation in ways we haven't yet modeled. Others point to supermassive black holes at galactic centers, whose extreme gravity could extend time-slowing effects far beyond their event horizons. The most intriguing possibility, time dilation and cosmic expansion might both be at play, their signals entangled in the light we receive. Like hearing an orchestra where 2 instruments play the same note, we'd need extraordinary precision to disentangle their contributions. Future telescopes measuring redshift in unprecedented detail might finally reveal whether Einstein's time-warping universe has been quietly impersonating an expanding one all along. Light doesn't always travel in a straight line, especially when the universe throws cosmic funhouse mirrors in its path. Picture this: a beam of light from a distant quasar skirts the edge of a colossal void, a region of space emptier than a desert at midnight. As the photon traverses this underdense expanse, it's not just dodging galaxies, it's navigating a gravitational landscape where space-time itself sags like a trampoline with missing springs. The result, the light's wavelength stretches, reddening as if the quasar were racing away, even if it's perfectly stationary. This isn't science fiction. It's the unsettling possibility that redshift, our gold standard for measuring cosmic expansion, might be partially, or entirely, a grand illusion woven by light's tortuous journey through the universe's hidden architecture. The math behind this cosmic sleight of hand is both elegant and unnerving. Einstein's general relativity predicts that light passing through regions of uneven mass distribution, like superclusters and voids, should experience integrated Sachs-Wolf and Rees-Symer effects. These mouthfuls describe how photons gain or lose energy depending on whether they're climbing out of gravitational wells or coasting through underdense regions. Scale this up across billions of light years, and the cumulative effect could mimic the very redshift patterns we attribute to universal expansion. Imagine a marathon runner alternating between uphill slogs and downhill sprints. Their final time might suggest a flat course, but the terrain tells a different story. Observational clues hint that this isn't just theoretical gymnastics. The cosmic microwave background, that fossilized glow from the universe's infancy, shows temperature dips around known supervoids, exactly what you'd expect if light reddens while crossing these regions. Even more provocative, some ultra-distant quasars appear anomalously red compared to their surroundings, as if their light traversed more than its fair share of cosmic potholes. Critics counter that these effects are too small to explain Hubble's law entirely. But here's the twist. We've barely mapped the large-scale structure of the universe beyond our local neighborhood. If voids are larger or more numerous than our surveys suggest, their redshift contributions could be far greater than models predict, the most radical implication. What we call dark energy, the mysterious force accelerating cosmic expansion, might be partially a mirage caused by light's journey through an evolving web of voids. As the universe ages, voids grow while superclusters thin out, creating an ever more extreme gravitational contrast. Light crossing this evolving landscape would redshift in ways that precisely mimic an accelerating universe, no dark energy required. It's like mistaking a funhouse mirror's warped reflection for your actual height. The measurement seems real, but the tool itself is distorting reality. This isn't to say expansion isn't happening at all. Rather, it's a wake-up call that the universe's greatest trick might be hiding its true nature in plain sight. Every redshift measurement we've ever taken could be a hybrid signal, part cosmic expansion, part gravitational hall of mirrors. Until we map the universe's structure in unprecedented detail, we're essentially interpreting a symphony while missing half the instruments. The next generation of telescopes, like the Vera Rubin Observatory, might finally tease apart these entangled signals, revealing whether our cosmic yardstick has been bending all along. Newton's law of gravity has ruled cosmology for centuries. Planets orbit, apples fall, and galaxies spin according to its elegant equations. But what if gravity itself changes its rules on cosmic scales? Enter modified Newtonian dynamics, or MUND, a theory that boldly suggests we've been misreading the universe's deepest forces. Instead of invoking invisible dark matter to explain why galaxies rotate faster than expected, MUND proposes a radical fix. Gravity doesn't weaken as sharply over distance as Newton or Einstein predicted. At extremely low accelerations like those in the outer reaches of galaxies, it clings on just a bit stronger. This tiny tweak could rewrite not just galaxy dynamics, but our entire interpretation of cosmic redshift. The implications are staggering. If gravity's pull defies expectations in faint outskirts of galaxies, might it also alter how light escapes them? Picture a photon fleeing a distant galaxy. Under MUND-adjusted gravity, space-time around that galaxy could warp differently than general relativity predicts, subtly stretching the photon's wavelength as it climbs free. Over billions of light-years, these microshifts might add up to the redshifts we observe. No universal expansion required. It's as if we've been measuring a mirage, mistaking gravity's secret adjustments for the universe's breadth. But does the math hold up? When astronomers pit MUND against telescope data, the results are a cosmic roller coaster. For spiral galaxies, MUND predicts rotation curves with uncanny precision, matching observed speeds without a shred of dark matter. Yet galaxy clusters, those massive cosmic metropolises, still seem to need extra invisible mass under MUND current equations. Even more damning, the cosmic microwave background's intricate patterns align neatly with standard cosmology's mix of dark matter and dark energy, leaving MUND scrambling for auxiliary hypotheses. Here's where it gets fascinating. MUND isn't alone in challenging gravity's rulebook. Tensor vector scalar gravity, or TVS, adds extra fields to spacetime, bending light in ways that could mimic expansion. Then there's emergent gravity, where gravity isn't a fundamental force but a side effect of quantum information buzzing through the cosmos. These theories share a thrilling premise. What if dark energy's accelerating universe is just gravity's shadow, cast by laws we're only beginning to glimpse? The real test lies in anomalies. Some ultra-diffuse galaxies' ghostly realms with almost no stars rotate as if governed by MUND rules, defying dark matter predictions. Elsewhere, the James Webb Space Telescope has spotted ancient galaxies too massive to form so early under standard cosmology, yet their redshifts align eerily with modified gravity models. Are these outliers flukes or hints of a deeper truth? Critics argue that tampering with gravity risks unraveling well-tested physics, from Mercury's orbit to gravitational waves. Yet history whispers caution. Einstein himself overthrew Newton by tweaking gravity's rules. Whether Mund or its cousins ultimately succeed, their greatest gift is the reminder that even our most trusted cosmic signals might be written in a language we've only half decoded. Every redshift measurement could be carrying two messages, one about the universe's expansion and another about gravity's hidden hand. What if light itself has an expiration date? Not fading like an old photograph, but slowly unraveling at the quantum level, photons shedding energy as they cross the cosmos like weary travelers losing steam over an impossible journey. This is the startling premise behind photon decay theories, where redshift isn't about expanding space or tired light, but about particles of light fundamentally breaking down over billions of years. Imagine a universe where even the most constant thing we know, the speed of light, isn't immune to time's erosion. The idea defies conventional wisdom. Photons are considered stable, massless particles that should persist unchanged across eternity. Yet some quantum gravity models suggest that at unimaginably long timescales, even photons might decay into lighter particles, perhaps hypothetical actions or even neutrinos. Each decay step would steal a fraction of the photon's energy, stretching its wavelength toward the red. The effect would be subtle. Over 1 million light-years, a photon might lose just 1 part in 100 trillion of its energy. But across cosmic distances, these vanishingly small losses could accumulate into the redshifts we observe, mimicking an expanding universe while the cosmos itself stands perfectly still. Evidence for this radical notion is thin but tantalizing. Certain high-energy gamma rays from distant blazars arrive slightly dimmer than expected, as if some of their photons leaked away during transit. Other hints come from the cosmic microwave background, where temperature fluctuations show patterns that could align with photon decay models better than standard cosmology. The most compelling argument, though, is philosophical. If all other particles eventually decay from unstable muons to hypothetical protons, why should light be the lone exception? Nature rarely grants perpetual free passes. Critics pounce on two glaring issues. First, photon decay would violate the conservation of energy, a cornerstone of physics. Proponents counter that energy might simply bleed into other dimensions or quantum fields, preserving the deeper laws while changing how they manifest in our universe. Second, and more damning, decaying photons should produce secondary particles we could detect, yet no telescope has found this predicted decay glow permeating space. Unless perhaps the decay products are invisible to our current instruments, like sterile neutrinos or dark sector particles, the most profound implication isn't just about redshift. If photons decay, then the universe's oldest light, the cosmic microwave background, might be younger than we think, its apparent age skewed by energy loss. Distant galaxies could be closer than their redshift suggests, rewriting the cosmic distance ladder. Even dark energy's purported acceleration might shrink into obscurity, revealed as a misinterpretation of light's slow unraveling. Whether photon decay ultimately holds up or not, it forces a humbling reckoning. Our entire cosmic map relies on light's faithfulness as a messenger. If that trust is misplaced, the universe we think we see might be a grand optical illusion, one fading gently into the red. The cosmic microwave background isn't just the oldest light in the universe, it's a frozen whisper from a time when everything was hotter, denser, and far more chaotic. This afterglow of the Big Bang blankets the sky in microwaves, its temperature varying by mere millionths of a degree. For decades, we've treated these fluctuations as cosmic hieroglyphs, spelling out the universe's expansion history. But what if we've been misreading the message? Hidden in those subtle ripples might be clues that redshift isn't just about space-time stretching, but something far more unexpected. Take those temperature variations, the slightly hotter and colder spots, mapping the early universe's density fluctuations. Standard cosmology interprets them as seeds for galaxy formation, stretched by inflation and later expansion. Yet some patterns defy expectations. Certain large-scale anomalies, like the cold spot spanning 1 billion light-years, appear too extreme for random chance. Could these be signatures of light interacting with unseen structures or forces during its 13 billion-year journey? One provocative theory suggests that if photons pass through vast cosmic textures, defects in space-time left over from the universe's fiery birth, they could emerge redshifted, no expansion required. It's as if the CMB isn't just a baby picture of the cosmos, but a palimpsest with layers of interference written across the eons. Even more intriguing are the CMB's polarization patterns, the faint swirls imprinted when light scattered off electrons in the infant universe. These B-mode polarizations, once hailed as smoking gun evidence for cosmic inflation, might carry alternative fingerprints. Some models show that if space has even a trace of conductive plasma left over ionized gas from early stars, it could subtly alter polarization while also redshifting light via plasma interactions. The kicker: this effect would grow stronger over time, potentially mimicking the accelerated expansion we attribute to dark energy. Then there's the Hubble tension, the growing discrepancy between how fast we measure the universe's expansion today versus predictions based on the CMB. Mainstream solutions tweak dark energy or neutrino counts, but fringe ideas go further. What if the CMB's redshift signals were contaminated by local phenomena? Imagine our solar system bobbing in a region of space slightly denser than average, like a ship in a gentle current. Light from the CMB passing through this Hubble bubble could redshift more than expected, skewing our entire cosmic timeline. Alternatively, if early universe physics differed just slightly, say, gravity weakened at ultra-high energies, the CMB's redshift patterns might encode a primordial adjustment to Einstein's equations, one that's been invisible until now. The most radical possibility: the CMB might not be a single snapshot at all. Some quantum gravity models suggest that what we call the cosmic microwave background could be a mosaic of light from slightly different epochs, its photons arriving via paths warped by spacetime's quantum foam. In this view, redshift variations aren't just cosmological, they're archaeological, revealing layers of cosmic history folded into a single image. Whether these ideas hold up or not, the lesson is clear: the CMB is more than a relic. It's a cipher, its subtle patterns a battleground for competing visions of reality. Every time we map its fluctuations with greater precision, we're not just refining our models, we're eavesdropping on a conversation between light and the universe's deepest secrets, one that's been ongoing since the dawn of time. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate illusionists, warping light so severely that even redshift becomes part of their trickery. Picture a supermassive black hole, its gravity so intense that spacetime cascades into it like water down a drain. Now imagine light struggling to escape that gravitational vortex. Photons clawing their way out don't just slow down, they lose energy, stretching into longer, redder wavelengths, like a climber exhausting themselves on an endless slope. This isn't just theoretical. We've seen it firsthand in the light from stars orbiting Sagittarius A, the Milky Way's central black hole. But here's the twist. What if these redshifted photons aren't just telling us about the black hole's immediate grip, but casting shadows that stretch across the cosmos? The math behind this is as mesmerizing as it is complex. Einstein's equations predict that near a black hole's event horizon, gravity bends light so severely that some photons orbit in loops before escaping, if they escape at all. This creates a phenomenon called the shadow, a dark silhouette against the backdrop of glowing accretion disks. But that shadow isn't static. As light fights free, its redshift becomes a fingerprint of the black hole's spin, mass, and even the structure of space-time itself. Some models suggest that for supermassive black holes in distant galaxies, this gravitational redshift could amplify the cosmological redshift we attribute to universal expansion. It's like mistaking a scream's echo for the voice itself. The original signal gets buried in the distortion. Observational clues hint at just how profound this effect might be. Take quasars, those brilliant beacons powered by voracious black holes. Some show emission lines redshifted far beyond what their host galaxies' distances suggest. Standard explanations invoke gas whirling at relativistic speeds, but alternative theories propose another culprit, the black hole's shadow stretching light before it even leaves the galactic core. Even more intriguing, the Event Horizon Telescope's images of M87's black hole revealed unexpected brightness asymmetries in its photon ring, subtle hints that redshift patterns around these monsters might not follow textbook predictions. The implications ripple outward. If black hole shadows contaminate redshift measurements even slightly, they could skew our cosmic distance ladder. Distant galaxies hosting active supermassive black holes might appear farther away than they truly are, their light doubly reddened by both expansion and gravitational shadows. This could explain anomalies like quasars with extreme redshifts nestled uncomfortably close to lower redshift galaxies, a cosmic oddity that currently forces astronomers to invoke improbable alignments. More radically, it suggests that dark energy's inferred acceleration might be partially an artifact, a mirage born from misreading light's battle with spacetime's darkest pits. Yet there's a catch. For black hole shadows to significantly impact cosmology, they'd need to be far more pervasive than we've observed. Most galaxies don't host actively feeding supermassive black holes, and even those that do might not magnify redshift enough to alter universal measurements. But what if we're underestimating their influence? Recent simulations show that quiet black holes, those not actively devouring matter, still warp spacetime enough to subtly redshift light passing near them. Scale this up across billions of galaxies, and the cumulative effect might be hiding in plain sight within our redshift surveys. The real revelation here isn't just about correcting measurements, it's about recognizing that the cosmos speaks in layered dialects. Redshift was never a single note. It's a chorus of gravitational echoes, Doppler shifts, and now perhaps the whispers of black hole shadows. As we peer deeper into these dark hearts, we're not just studying monsters. We're decoding the universe's most cunning camouflage, one stretched photon at a time. Magnetism isn't just for fridge stickers and compass needles. It's woven through the fabric of the cosmos itself. Between galaxies, vast magnetic fields stretch for millions of light years, invisible threads humming with energy. We've long known these fields bend charged particles, sculpting cosmic rays into spirals. But here's the kicker. What if they're also gently tweaking the light passing through them, stretching its wavelength just enough to mimic cosmic expansion? This isn't science fiction. The physics behind it is as real as the auroras dancing over Earth's poles, only scaled up to galactic proportions. Think of a photon traveling through intergalactic space like a kayak crossing a river with hidden currents. Normally, light ignores magnetic fields because it carries no charge. But if even a tiny fraction of photons interact with the ionized gas swirling through these fields, say by scattering off electrons gyrating along magnetic lines, they could lose energy over epic distances. Each microscopic nudge might be negligible, but over billions of years, those interactions could add up to the redshifts we've blithely attributed to an expanding universe. It's as if the cosmos has been quietly running a magnetic marathon, and we've mistaken its fatigue for flight. The evidence is tantalizing. Radio telescopes have mapped faint magnetic fields threading galaxy clusters, some with strengths up to 1/1,000,000th of Earth's field, weak by human standards but pervasive enough to matter cosmically. Even more compelling, certain quasars show polarized light patterns that suggest magnetic fields have twisted their photons during transit. Then there's the mystery of ultra-high-energy cosmic rays, which arrive with trajectories seemingly bent by large-scale magnetic structures we can't yet see. If these fields can alter particles with 1,000,000,000,000 times more energy than visible light, might they also leave fingerprints on ordinary starlight? Critics counter that for magnetism to explain redshift fully, the universe would need far stronger fields than we've detected. But here's where it gets wild. Some theories propose that primordial magnetism left over from the universe's first seconds could have seeded fields now hidden in cosmic voids, their presence revealed only by their subtle influence on light. Others suggest that dark matter, if it has even a whisper of electromagnetic interaction, might generate magnetic effects on scales we're only beginning to probe. The most radical implication, magnetism could be skewing our cosmic measurements in ways we haven't accounted for. If distant galaxies appear redder because their light traversed magnetized voids, not because they're racing away, our entire expansion narrative might need recalibrating. It's a reminder that the universe rarely reveals its secrets through just one lens. Every redshift measurement we take could be a palimpsest written not just in the ink of cosmic expansion, but in the invisible ink of magnetism's quiet hand. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, yet you'd never know. These nearly massless particles zip through planets, stars, and entire galaxies as if they weren't even there, interacting so weakly with matter that detecting them requires underground labs filled with swimming pool-sized tanks of ultra-pure water. But here's the cosmic curveball. What if these spectral particles, despite their elusive nature, are quietly tweaking the light traveling across the universe? What if redshift isn't just about expanding space or tired photons, but about neutrinos leaving faint fingerprints on starlight over billions of years? The math behind this idea stretches the limits of particle physics. Normally, neutrinos and photons ignore each other like strangers passing in the night. But at extremely high energies, the kind found near pulsars or colliding galaxy clusters, neutrinos could theoretically interact with photons through quantum loops or hypothetical force carriers we haven't yet discovered. Each interaction would be vanishingly rare, but over cosmological distances, even a 1 in a trillion chance adds up. Picture a beam of starlight crossing a neutrino-rich region near a supernova remnant. If just a few photons scatter off neutrinos in flight, they'd lose a whisper of energy, redshifting imperceptibly. Scale this up across millions of galaxies, and suddenly, the universe's redshift tapestry might carry threads woven by these ghostly particles. Evidence for this remains speculative, but tantalizing clues linger. IceCube, the neutrino observatory buried in Antarctic ice, has detected high-energy neutrinos from distant blazars, active galaxies with jets pointed straight at Earth. Some of these neutrinos arrive with energies so extreme that standard models struggle to explain their production. Could their journey have involved interactions with light itself? Even more intriguing are anomalies in gamma-ray bursts, where certain high-energy photons seem to arrive slightly delayed compared to their lower-energy counterparts. One explanation: neutrino photons scattering during transit, subtly altering the light's energy and speed. Critics argue that for neutrinos to significantly impact redshift, their interaction cross-section would need to be far higher than current physics allows. But here's where quantum weirdness kicks in. If neutrinos have even a tiny magnetic moment, a property allowing them to interact with electromagnetic fields, they could mediate photon energy loss in ways we haven't yet modeled. Alternatively, if sterile neutrinos exist hypothetical cousins to the ones we know, they might interact just enough to redshifting starlight without betraying their presence in particle colliders. The most mind-bending implication: neutrino-induced redshift wouldn't be uniform. Regions brimming with neutrinos, like galaxy clusters or the wakes of gamma-ray bursts, might show exaggerated redshifts, while voids appear comparatively untouched. This could explain oddities like galaxies with mismatched redshifts or quasars that seem too bright for their cosmological distance. Instead of a perfectly expanding universe, we might be seeing a patchwork quilt of light altered by invisible hands. Whether this hypothesis holds up or not, it underscores a profound truth. The universe's quietest actors might be its most influential. If neutrinos, the closest thing to nothing we've ever detected, can shape our cosmic measurements, then every redshift we observe could be a message, not just from fleeing galaxies, but from the ghosts threading the space between them. What if the very building blocks of reality aren't as constant as we think? For centuries, physics has treated particle masses like cosmic keystones, unchanging and universal. But imagine a universe where electrons, photons, or even quarks subtly shift their weight over billions of years. This isn't just a thought experiment. Variable mass theories suggest that if particles gained mass as the cosmos aged, the light emitted by ancient stars and galaxies would redshift, not because space is stretching, but because the rules of the game were different when that light began its journey. Take the photon, that massless messenger of light. Most models assume it's always weighed nothing, but some extensions of quantum physics allow for photons to acquire a tiny mass in certain conditions, like passing through exotic fields or extra dimensions. Even a minuscule shift would have dramatic consequences. A massive photon wouldn't travel at light speed anymore. It would slow down, losing energy and stretching its wavelength over cosmic distances. The effect would be indistinguishable from cosmological redshift, like mistaking a slowing marathon runner for one moving away. Electrons offer another tantalizing lever. Their mass governs how atoms absorb and emit light, setting the spectral lines we use to measure redshift. If electrons were lighter in the early universe, those lines would form at slightly different energies, skewing our measurements. Picture a piano where the keys subtly retune over centuries. Music played on it centuries ago would sound off-pitch today, even if the recording itself hadn't changed. Similarly, ancient starlight might carry a false redshift, not from cosmic expansion, but from atomic physics operating by different rules. The math behind these ideas walks a tightrope. To mimic observed redshifts, particle masses would need to evolve at precise rates, fast enough to affect distant light, but slow enough to leave local physics untouched. Some theories achieve this by tying mass to the universe's expansion, like a cosmic dial turning with space-time itself. Others invoke symmetries breaking as the cosmos cools, freezing particle masses into their current values. Remarkably, certain grand unified theories predict such shifts naturally, with particles shedding mass like winter coats as the universe transitions between phases. Critics highlight two glaring challenges. First, varying masses would disrupt exquisitely tuned processes like stellar nucleosynthesis, the alchemy that forges elements in stars. If electrons were lighter in the past, stars would burn fuel differently, potentially altering the universe's chemical makeup. Yet here's the twist. Some metal-poor stars in the Milky Way show odd abundance patterns that defy standard models, hinting that physics might indeed have drifted over time. Second, experiments like the Large Hadron Collider constrain how much particle properties can vary. But these tests probe limited epochs, like snapshots of a river that may have flowed differently in its distant past. The most radical implication: if mass variability is real, our cosmic expansion measurements could be doubly misleading. Not only might redshift reflect changing particle physics rather than space-time stretch, but the very matter composing our telescopes could have subtly shifted, warping our calibration. It's a hall of mirrors scenario where both the observed and the observer are in motion. Whether variable mass theories ultimately hold up or not, they force a humbling realization: the universe's constants might be less constant than we thought. Every redshift measurement we've ever taken could be carrying two stories, one about the cosmos expansion and another about the quiet metamorphosis of reality's deepest rules. Entropy isn't just about messy rooms or melting ice cubes. It might be the hidden force shaping the cosmos itself. Picture gravity not as a fundamental force, but as a side effect of the universe's relentless slide toward disorder, like a cosmic game of marbles rolling downhill to the lowest energy state. This radical idea, known as entropic gravity, suggests that what we perceive as gravity's pull could actually be spacetime's way of maximizing entropy, much like heat naturally flowing from hot to cold. But here's where it gets truly mind-bending. If gravity emerges from entropy, could redshift, the very phenomenon we use to map cosmic expansion, be another echo of the universe's deep thermodynamic dance? The connection hinges on holography, a principle suggesting that all the information in a volume of space might be encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. In this view, every galaxy, star, and photon exists within a cosmic hologram, where entropy governs not just particles but the fabric of space-time itself. As light travels across this holographic landscape, it doesn't just pass through space, it interacts with the entropy gradients woven into reality's structure. Each interaction could subtly sap the photon's energy, stretching its wavelength over billions of years. The result, a redshift that looks like cosmic expansion, but might instead be the universe's thermodynamic signature, written in light. Evidence for this is speculative but tantalizing. Black holes, those entropy powerhouses, exhibit redshift patterns at their edges that align eerily with entropic gravity predictions. Even more provocative, the cosmic microwave background's temperature fluctuations, those faint wrinkles from the early universe, mirror the patterns you'd expect if entropy were sculpting spacetime on the largest scales. Critics argue that entropic gravity struggles to match the precision of Einstein's general relativity, especially in extreme environments like neutron star mergers. Yet proponents counter that relativity and thermodynamics might be two sides of the same coin, with redshift bridging the gap between the microscopic and cosmic. Imagine the implications. If entropy drives both gravity and redshift, dark energy's accelerating expansion might not be a mysterious force at all, just the universe settling into its most probable disordered state, like a gas filling a room. Distant galaxies wouldn't be fleeing from us, their light would simply be unraveling into the cosmos' thermodynamic equilibrium. It's a reminder that the universe's grandest phenomena might not be fundamental forces, but emergent stories told by countless tiny steps toward chaos. Every redshifted photon could be less a measure of distance and more a testament to entropy's quiet, universal reign. Fractals aren't just mesmerizing patterns in math textbooks, they might be the hidden blueprint of the cosmos itself. Picture a universe where galaxies cluster into superclusters, which themselves form larger structures, repeating the same basic architecture across scales like a set of Russian nesting dolls. This fractal cosmology turns mainstream astronomy on its head, suggesting that redshift doesn't require universal expansion, just light navigating an endlessly recursive cosmic labyrinth where every turn reveals another layer of self-similar structure. The idea springs from an unsettling observation. Galaxy surveys keep revealing unexpected clumping at ever larger scales. The Sloan Digital Sky Survey mapped millions of galaxies, expecting to find smooth distribution as standard cosmology predicts. Instead, it uncovered vast filaments and voids repeating in patterns that look eerily like fractal geometry, the same branching structures seen in lung tissue, river deltas, and even financial markets. If matter organizes this way, light traveling through these nested layers would encounter gravitational wells at every scale, redshifting slightly each time it climbs free. Over billions of light-years, these microshifts could mimic Hubble's law perfectly, no expanding space-time required. It's as if we've been measuring the universe's wrinkles and mistaking them for its breadth. Critics argue that fractal models struggle to explain the cosmic microwave background's smoothness or the precise ratios of light elements forged in the Big Bang. But proponents counter with startling simulations. When physicists program supercomputers to model universe formation without assuming uniformity, fractal-like structures emerge naturally from gravitational collapse. Some even reproduce the observed redshift distance relation purely through hierarchical clustering, no expansion baked into the code. The kicker: these models also predict subtle anomalies in galaxy motions that match puzzling real-world observations, like entire galaxy streams moving coherently against the expected cosmic flow. The most radical implication isn't just about redshift. If the universe is fractal, its total mass could be far greater than we've estimated, with most matter hidden in the folds of unseen scales. Dark matter might not be missing, just distributed in patterns we've failed to recognize. Even dark energy's apparent acceleration could be an illusion, a miscalibration from assuming homogeneity where none exists. Whether fractal cosmology ultimately holds up or not, it forces a profound rethink of our place in the cosmos. Instead of a lone bubble of matter adrift in expanding emptiness, we might inhabit one layer of an infinite cosmic tapestry, where every redshift measurement carries echoes of the universe's hidden symmetries written in light. The holographic principle flips reality inside out. What if the three-dimensional universe we think we inhabit is just a shadow cast by a two-dimensional surface at the edge of everything? This isn't science fiction. It's a serious hypothesis born from black hole physics, where the information swallowed by these cosmic pits seems to be encoded on their event horizons like data on a cosmic hard drive. Now take that idea and scale it up to the entire cosmos. If our 3D universe is a projection from some vast 2D boundary, then redshift might not be about galaxies moving at all. It could be a glitch in the cosmic code, a side effect of light traveling through what's essentially an illusion. Picture a movie theater where the images on screen look three-dimensional, but they're actually projected from a flat film reel. Now imagine that reel is the true fabric of reality, and everything we see, stars, galaxies, even our own bodies, are just holographic reconstructions. In this view, redshift becomes an artifact of the projection process. As light crosses the holographic screen, subtle pixelation at the quantum scale could stretch its wavelength, like a video buffering over a slow connection. The farther the light travels, the more it degrades, creating the illusion of cosmic expansion when in reality, we're just seeing the limits of the universe's rendering power. The math behind this is both elegant and bizarre. String theorists discovered that equations describing physics in a 3D space can perfectly match those on a 2D boundary, a duality suggesting our 3D experience might be secondary. Apply this to cosmology, and light's journey takes on new meaning. Photons aren't traversing expanding space. They're navigating information transfers between dimensions, with each transfer sapping a bit of energy. This could explain why redshift increases smoothly with distance, not because space stretches uniformly, but because more holographic processing steps distort light over longer paths. Evidence is scarce but tantalizing. The cosmic microwave background's temperature fluctuations follow patterns that some theorists argue align better with holographic models than standard inflation. Even more provocative, certain quantum gravity simulations show that emergent space-time, the idea that space isn't fundamental but arises from deeper information processing, naturally produces redshift-like effects without any expansion baked into the equations. Critics argue that holography struggles to explain why distant supernovae appear dimmer than expected, a key pillar of dark energy evidence. Yet proponents counter that if the holographic pixel size changes over cosmic time, perhaps as the universe's underlying code evolves, it could mimic accelerating expansion without any dark energy required. The most mind-bending implication: if the holographic principle is real, then every redshift measurement we've ever taken isn't just mapping galaxies. It's tracing the edges of reality itself, revealing where the projection phrase and the true, flat nature of existence peeks through. The cosmos might not be expanding after all. We could be watching the ultimate optical illusion, a cosmic sleight of hand where light's stretch is the telltale clue that we're living inside the universe's grandest magic trick. Light doesn't always take the shortest path. Sometimes it takes the scenic route. In a universe riddled with warped space-time, photons might twist and turn like hikers navigating a mountain range, their journey stretching far longer than a straight line would suggest. This isn't just a detour, it's a cosmic sleight of hand where the extra distance traveled could stretch light's wavelength, creating redshift without a single galaxy moving away. Picture a beam of light skirting the edge of a black hole, spiraling through its gravitational whirlpool before breaking free. By the time it reaches us, that light isn't just bent, it's exhausted, its waves elongated as if it crossed a universe far larger than the one we see. The math behind this is both elegant and mind-bending. General relativity tells us massive objects don't just bend light's path, they stretch the very fabric of time around them. A photon passing through these warped regions experiences a kind of temporal drag, like a car slowing on a winding road. Over cosmic distances, these micro-delays compound, making the light appear redshifted purely because its journey was more circuitous than we assumed. It's as if we've been measuring the universe with a stretched tape measure, mistaking the wrinkles in space-time for expansion itself. Evidence for this hides in plain sight. Gravitational lensing, where massive galaxy clusters bend light like a funhouse mirror, already proves space-time isn't flat. Some lensed quasars arrive with slightly different redshifts depending on which path their light took around the cluster, a discrepancy standard cosmology chalks up to relative motion. But what if the longer path genuinely stretched the light? Even more telling are galaxies whose light curves around cosmic voids, vast, empty regions where space-time sags like a trampoline missing springs. Light skirting these voids travels farther, emerging redder than expected, as if the void itself imprinted extra redshift onto the photons. The implications rewrite cosmic cartography. If non-standard paths contribute significantly to redshift, then the universe's expansion might be slower than we think, or even static, with warped geometry fooling our measurements. Distant supernova could appear dimmer not because they're accelerating away, but because their light zigzagged through a maze of invisible space-time folds. Even the Hubble constant, the rate of cosmic expansion, might need recalibrating, its value skewed by light's indirect routes. Critics argue that for twisted paths to explain redshift fully, the universe would need far more extreme space-time curvature than we've observed. But here's the catch: we've only mapped the tip of the cosmic iceberg. Dark matter's invisible tendrils and primordial gravitational waves could be warping space in ways our telescopes can't yet detect. Simulations of cosmic web filaments, those sprawling highways of galaxies and dark matter, show that even subtle undulations in space-time could redirect light over billions of years, subtly altering its energy. The real revelation: redshift might not be a single phenomenon, but a layered signal-part expansion, part space-time's hidden topography. Every photon reaching our telescopes could carry not just the story of distant galaxies, but the secret contours of the universe's twisted backroads, written in the language of stretched light. Dark energy and dark matter have always been the universe's most elusive suspects, two invisible forces shaping the cosmos in ways we can't fully explain. But what if they're not separate entities at all? Enter dark fluid, a radical theory that merges them into a single, dynamic substance capable of morphing its behavior over cosmic time. Imagine an exotic medium filling the void, one that exerts gravity like dark matter in some regions while pushing space apart like dark energy in others. This chameleon-like fluid wouldn't just influence the universe's expansion, it might be quietly tweaking the light passing through it, imprinting redshift without the need for traditional stretching of space. The mechanics are as elegant as they are speculative. Picture a cosmic ocean where pressure dictates the rules. In denser regions around galaxies and clusters, this dark fluid could behave like a gravitational glue, mimicking dark matter's pull. But in the vast, empty voids between galaxies, the same fluid might switch roles, its negative pressure driving cosmic acceleration like dark energy. Now imagine light traversing this shifting landscape. As photons navigate areas where the fluid's pressure fluctuates, they could lose energy to the medium itself, like sound waves fading as they cross from water to air. Over billions of light years, these subtle interactions might accumulate into the redshift patterns we've attributed to expansion. It's as if the universe has been playing a game of cosmic sleight of hand, using a single dark substance to mimic two separate phenomena and fooling us in the process. Critics highlight two major hurdles. First, dark fluid models struggle to explain the precise clustering of galaxies observed in surveys like the Sloan Digital Sky Survey, which align neatly with traditional dark matter simulations. Second, there's the cosmic microwave background. Its temperature fluctuations fit the standard two-component model of dark matter and energy with exquisite precision. Yet proponents counter with intriguing tweaks. Some versions of dark fluid theory incorporate quantum effects, allowing the substance to exhibit superfluid properties at galactic scales, which could better match observations. Others suggest that dark fluid's pressure variations might leave subtle imprints in the polarization patterns of the cosmic microwave background, imprints next-generation telescopes could soon detect. The most tantalizing clue comes from an unexpected place: the Hubble tension. This growing discrepancy in measurements of the universe's expansion rate might find a natural resolution if dark fluid's properties evolved over time, altering how redshift accumulates across different cosmic epochs. It's a reminder that the universe rarely adheres to our neat categorizations. What we've called dark matter and dark energy might just be two faces of a deeper, stranger reality, one where redshift isn't just a measure of distance, but a cipher hiding the true nature of the cosmos' hidden scaffolding. Quantum entanglement defies everything we think we know about distance. Particles separated by galaxies can influence each other instantly, as if space between them doesn't exist. Now imagine this spooky action at a distance isn't just a microscopic curiosity, but a cosmic phenomenon shaping the light we use to measure the universe. What if entangled particles woven through the fabric of space-time itself are subtly tweaking the properties of photons as they travel billions of years to reach us? This isn't just wild speculation. At the intersection of quantum mechanics and cosmology lies a provocative idea. Entanglement might be quietly scripting part of Redshift's story. Picture two entangled photons born in the early universe, their fates linked no matter how far apart they drift. One gets absorbed by a distant galaxy, while the other barrels toward Earth. According to quantum theory, any change to the absorbed photon, like interacting with matter, could instantaneously alter its entangled twin mid-flight. These subtle adjustments might nudge the arriving photon's energy, shifting its wavelength ever so slightly toward the red. Over cosmic distances, countless such interactions could accumulate, mimicking the redshift we attribute to universal expansion. It's as if the universe has been whispering to light through hidden quantum channels, leaving fingerprints we've mistaken for cosmic motion. The math behind this is as beautiful as it is bizarre. Quantum field theory suggests that vacuum fluctuations, those fleeting particle-antiparticle pairs popping in and out of existence, could mediate entanglement across vast scales. Photons traveling through this frothy quantum sea might encounter regions where entangled pairs imprint their state onto passing light, like ripples crossing in a pond. Some models show that if even a tiny fraction of photons experience this effect, it could skew redshift measurements by the precise amount we've chalked up to dark energy's influence. Evidence remains elusive, but tantalizing hints linger. Certain anomalies in quasar spectra, unexpected correlations between light from galaxies separated by billions of light years, align eerily with predictions from entanglement-based redshift models. Even more striking, the cosmic microwave background's polarization patterns show statistical quirks that some theorists argue could reflect large-scale quantum correlations imprinted during the universe's first moments. Skeptics counter that maintaining entanglement across cosmic distances seems impossible to coherence. The tendency of quantum systems to unravel should erase such effects long before light reaches us. Yet proponents point to black holes whose event horizons might protect entanglement by preventing information loss, or to holographic principles where entangled states are encoded on the universe's boundary, immune to local disruption. The implications rewrite cosmology's rulebook. If entanglement contributes to redshift, then the universe's apparent acceleration might be an illusion, a quantum hall of mirrors where light's journey is shaped by invisible connections threading the cosmos. Distant galaxies could be closer than their redshift suggests, their light not stretched by expanding space but nudged by the universe's hidden quantum handshake. It's a reminder that reality's deepest layers might not play by the rules we've written, and that the light we've used to map the cosmos could be carrying messages from a quantum realm we're only beginning to fathom. Primordial black holes sound like something from a physicist's fever dream, tiny, ancient monsters lurking in the darkness, relics from the universe's first chaotic moments. Unlike their supermassive cousins that anchor galaxies, these could be as light as an asteroid or as heavy as a star, scattered across the cosmos in vast, invisible swarms. But here's where it gets wild. If these primordial predators exist in enough numbers, their combined gravity might be bending light in ways we've mistaken for cosmic expansion. Imagine trillions of black holes, each no wider than a city block, weaving a gravitational web so dense that photons passing through it emerge stretched and weary like runners navigating an obstacle course that steals their energy with every step. The theory hinges on a cosmic sleight of hand. According to general relativity, any mass warps space-time, and light traversing that warped terrain gets redshifted. Normally, we think of this effect as localized, like the slight reddening of starlight skirting the edge of a star, but scale it up to countless black holes peppered throughout intergalactic space, and suddenly, the collective gravitational pull could mimic the smooth redshift gradient we attribute to universal expansion. It's not that galaxies are racing away. It's that their light is being subtly sapped by an unseen archipelago of miniature black holes, each tugging at photons like invisible hands plucking at a cosmic harp. Evidence for this is tantalizingly indirect. Some astrophysicists point to odd gaps in the cosmic microwave background, tiny, unexplained cold spots that could be shadows cast by primordial black hole clusters. Others highlight mysterious gravitational lensing events, where distant stars flicker as if something too small and dark to see is drifting in front of them. Then there's the puzzle of missing baryonic matter. The universe seems to have less visible stuff than calculations predict. Could primordial black holes be hiding that missing mass, their gravity redshifting light while remaining effectively invisible? Critics raise valid concerns. For these black holes to explain redshift fully, they'd need to be distributed with near-perfect uniformity. Any clumping would distort starlight unevenly, creating patches of exaggerated redshift we don't observe. Yet proponents counter that quantum fluctuations in the early universe might have spread them evenly, like seeds scattered by a cosmic wind. Even more intriguing, certain models suggest that primordial black holes could evolve over time, merging or evaporating in ways that maintain the delicate balance needed to mimic Hubble's law. The implications are staggering. If primordial black holes contribute significantly to redshift, our cosmic expansion measurements might be double counting gravity's role. Dark energy's apparent acceleration could shrink or vanish entirely, revealing a universe far stranger and more crowded than we'd imagined. Every redshifted photon might carry not just the story of distant galaxies, but the ghostly imprint of a hidden population of ancient black holes, their collective whisper woven into the fabric of light itself. What if the universe's rulebook isn't written in permanent ink? For centuries, we've treated the fine structure constant, that fundamental number governing how light and matter interact, as an unchanging pillar of reality. But hidden in the light of quasars, those brilliant beacons at the edge of space-time, might be evidence that this constant has been quietly shifting over billions of years. And if that's true, it wouldn't just tweak our physics textbooks, it would unravel how we interpret cosmic redshift entirely. The fine structure constant, often abbreviated as alpha, is a cocktail of nature's most basic ingredients: the speed of light, the charge of an electron, and Planck's constant. Together, they dictate how tightly atoms cling to their electrons, how stars forge elements, even how light bends around galaxies. For decades, we've assumed alpha stayed fixed across time and space. But in the late 1990s, a team analyzing quasar light stumbled onto something bizarre. The absorption lines, those dark fingerprints left when distant gas clouds soak up specific wavelengths, appeared slightly out of place. Not by much, just a few parts in a million, but the pattern suggested alpha might have been smaller when the universe was young. Here's where redshift gets turned on its head. If alpha truly varies, then the light we receive from ancient quasars isn't just stretched by cosmic expansion. it's also carrying encoded changes in the very laws of physics. Picture a piano where the keys subtly retune themselves over centuries. Music played on it long ago would reach our ears off-pitch, even if the instrument hadn't moved an inch. Similarly, if alpha was different when a quasar emitted its light, the wavelengths we measure today would be skewed, masquerading as additional redshift. The implications ripple through cosmology like a shockwave. First, it means our cosmic distance ladder, the tool we use to map the universe's expansion, might be wobbling on unstable foundations. If part of the redshift we attribute to galaxies fleeing from us actually comes from drifting constants, then dark energy's grip on the cosmos could be weaker than we think. Even more radical, some theories suggest alpha's variation could be tied to extra dimensions or exotic dark energy fields, meaning redshift anomalies might be our first glimpse of physics beyond Einstein's relativity. Critics aren't convinced. Repeating the quasar measurements with newer telescopes, some teams found no evidence of alpha's variation, chalking up the original result to systematic errors. Yet intriguingly, certain metal-poor stars in the Milky Way show atomic transitions that deviate from expectations, as if alpha's value flickered in localized pockets of space. Then there's the Oklo Natural Nuclear Reactor, a 2-billion-year-old uranium deposit in Africa where fossilized neutron reactions suggest alpha might have been slightly different in Earth's past. The debate rages, but the lesson is clear. Redshift isn't just a yardstick for cosmic expansion. It's a cosmic palimpsest layered with clues about whether the universe's deepest rules are as immutable as we believe, or whether they've been quietly rewriting themselves all along. Cosmic strings sound like something from a physicist's wildest dreams, one-dimensional scars in space-time, thinner than a proton yet stretching across the entire universe. These hypothetical relics, theorized to have formed in the first split second after the Big Bang, aren't just cosmic curiosities. They could be vibrating like guitar strings under unimaginable tension, sending ripples through space-time that subtly tweak the light passing by. Imagine a beam of starlight skimming past one of these invisible filaments. As the string vibrates, its gravitational wake would stretch and compress space-time around it, warping the photon's wavelength like a ship bobbing in choppy seas. Over billions of light-years, these microshifts could add up to measurable redshifts, ones we've blindly attributed to cosmic expansion. The math behind this is both elegant and eerie. Cosmic strings, if they exist, would pack the mass of a mountain range into a length smaller than an atom. Their vibrations wouldn't just bend light, they'd create kinks and cusps in space-time where energy concentrates, potentially emitting bursts of gravitational waves. Some models suggest these vibrations could imprint specific patterns on the cosmic microwave background, subtle, linear temperature variations that next-generation telescopes might soon detect. Even more tantalizing, certain anomalous galaxy alignments, where distant quasars seem to line up in suspiciously straight chains, could be the ghosts of cosmic strings warping the light from objects behind them. Hunting these spacetime scars isn't science fiction. Astronomers have already scoured the sky for their signatures, searching for telltale double images of galaxies split by a string's gravity or abrupt jumps in the cosmic microwave background's temperature. So far, the search has come up empty, but that hasn't killed the theory. Cosmic strings could be rarer or fainter than we've predicted, their vibrations too subtle for current instruments to catch. Or perhaps they've decayed over time, leaving only faint echoes in the redshift patterns we've already mapped. The most radical implication: if cosmic strings contribute to redshift, their vibrations might be hiding in plain sight within our existing data. The universe's expansion could be slower than we think, with these ancient space-time defects masquerading as additional stretching. It's a reminder that the cosmos often writes its secrets in codes we're still learning to read, and that the redshift we've used to map the universe might be carrying messages from the very dawn of time, etched in the tremors of invisible strings. Space might not be the empty stage we imagine. It could be a shimmering illusion, a hologram projected from some deeper quantum reality. This radical idea, known as emergent space-time, suggests that what we perceive as the three-dimensional universe isn't fundamental at all. Instead, it bubbles up from a hidden network of quantum information, like the 3D world of a video game emerging from lines of binary code. If true, then redshift, the cosmic signal we've used to map the expanding universe, might not be about stretching space at all, but about light navigating a reality that's pixelated at scales we can't yet see. Picture a beam of light traveling across the cosmos. In standard physics, it glides through smooth, continuous space. But if space emerges from quantum bits, that journey becomes far stranger. Each step the photon takes could be more like hopping between discrete nodes in a vast cosmic network, with every interaction subtly altering its energy. Over billions of light years, these tiny shifts might accumulate, stretching the photon's wavelength in a way that perfectly mimics the redshift we attribute to universal expansion. It's as if we've been measuring the universe with a ruler that's secretly made of rubber, its markings changing as we go. The math behind this is both elegant and mind-bending. In some quantum gravity models, spacetime's emergence resembles how temperature arises from the chaotic motion of molecules, a collective effect with no single source. Photons traveling through this pixelated landscape would experience something akin to computational lag, their wavelengths reddening as they navigate the underlying code's processing limits. Remarkably, certain simulations show this could reproduce Hubble's law, the relationship between redshift and distance without any actual expansion baked into the equations. Instead, the redshift becomes a side effect of light's journey through a universe where space itself is stitched together from something deeper. Clues for this wild idea hide in unexpected places. The cosmic microwave background's temperature fluctuations, those faint wrinkles from the universe's infancy, show patterns some theorists argue align better with emergent spacetime models than with traditional inflation. Even more provocative, black holes might be giving us direct hints. Their event horizons appear to encode information in a way that mirrors a 2D surface, as if the 3D universe is literally projected from its boundaries. If spacetime is indeed a hologram, then redshift could be less about galaxies moving and more about the cosmic projector's resolution degrading over distance. Critics argue that emergent spacetime struggles to explain why distant supernovae appear dimmer than expected, a key piece of evidence for cosmic acceleration. Yet proponents counter with a breathtaking possibility. What if dark energy isn't a force but an artifact? If the universe's underlying pixels grow coarser over time, light crossing larger volumes would naturally lose energy, mimicking the effect of an expanding space. No mysterious repulsive force required, just the universe's hidden quantum architecture revealing itself through light's slow fade to red. The real magic of this idea isn't just in rewriting redshift's meaning, it's in reimagining reality itself. If space emerges from quantum information, then every photon reaching our telescopes carries not just the story of distant stars, but the secret language of the cosmos' deepest layer. The night sky becomes a flickering screen, and redshift, just the universe's way of reminding us we're all living inside the ultimate simulation. Gravity isn't the only invisible hand shaping the cosmos, there might be others we've yet to name. For centuries, physics has operated with four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But lurking in the equations of quantum mechanics and cosmology are hints of a possible fifth force, an exotic interaction that could subtly alter light's journey across the universe. Picture a photon traveling through what we think is empty space, only to encounter an unseen field tugging at its energy like an invisible current. Over billions of light years, this gentle, persistent pull could stretch the photon's wavelength, creating the illusion of cosmic expansion when in reality, light is simply being sapped by forces beyond our current understanding. The idea isn't as far-fetched as it sounds. In the hunt for dark matter, physicists have proposed various fifth force candidates, particles or fields that interact so weakly with ordinary matter they've eluded detection. Take the hypothetical dark photon, a counterpart to the light-carrying photons we know, but one that mediates interactions in the hidden dark sector. If dark photons exist, they might influence ordinary light through subtle interference, gradually transferring energy away from visible photons as they traverse the cosmos. Another candidate is the quintessence field, a dynamic form of dark energy that could vary in strength across space and time, imprinting redshift patterns that mimic an accelerating universe. Then there's the chameleon particle, a theoretical entity that changes its properties depending on its environment. In the dense heart of a galaxy, it might behave like a lightweight, short-range force, while in the emptiness of intergalactic space, its effects could stretch across vast distances. If light interacts with this chameleon field during its journey, the resulting energy loss could perfectly replicate the redshift we attribute to universal expansion. Some models even suggest that this fifth force could be tied to extra dimensions, hidden layers of reality where gravity or other interactions play by different rules, leaking their influence into our observable universe through redshift anomalies. Critics argue that introducing a fifth force complicates physics without definitive proof, but the evidence or lack thereof is intriguing. Certain astronomical surveys have detected puzzling galaxy motions that defy predictions based on known gravity alone, as if unseen forces are nudging celestial bodies off their expected path. Even more provocative, lab experiments using ultra-sensitive torsion balances have reported anomalous forces at microscopic scales, though these results remain controversial. If these effects are real, they could hint at a fifth force operating in the shadows, one that scales up to cosmological distances and leaves its mark on redshift measurements. The implications rewrite our cosmic narrative. If a fifth force contributes to redshift, then dark energy's role in accelerating the universe might need re-evaluation or even retirement. Distant galaxies could be closer than their light suggests, their apparent flight an illusion crafted by an unknown interaction. It's a humbling reminder that the universe's greatest mysteries might not lie in the distant reaches of space, but in the gaps of our understanding, waiting for the next revolutionary idea to shine a light on what we've missed. Every redshifted photon could be carrying not just the story of an expanding cosmos, but the whisper of forces we're only beginning to imagine. Imagine two soap bubbles floating toward each other in slow motion, their surfaces shimmering with unseen energy. Now picture those bubbles as entire universes, each with its own laws of physics, drifting through a higher dimensional void we can't perceive. When they touch, the collision wouldn't just create cosmic ripples, it could send shockwaves through space-time itself, warping light in ways that mimic the redshift we've attributed to expansion. This isn't just theoretical poetry. Multiverse models suggest that if our universe even gently grazed another, the encounter could leave behind redshift anomalies, sudden spikes or dips in the cosmic lightscape, like fingerprints from a reality beyond our own. The mechanics of such a collision defy everyday intuition. In brane cosmology, a branch of string theory, our universe might be a three-dimensional membrane floating in a higher dimensional bulk. Other branes could drift through this bulk like sheets in a cosmic dryer, occasionally brushing against one another. When they do, the energy released wouldn't just create a localized event like a Big Bang. It could send a pressure wave racing through both universes, stretching or compressing space-time in its wake. Light crossing these warped regions would emerge redshifted or blue-shifted, not because its source is moving, but because the very fabric of its reality has been dented by an encounter with another cosmos. Clues to these cataclysmic handshakes might already hide in our sky. Astronomers have spotted curious, cold spots in the cosmic microwave background, regions slightly cooler than their surroundings that defy standard inflationary explanations. One provocative theory suggests these could be bruises from a long-ago collision with a parallel universe, where the energy of impact siphoned away heat from our cosmos. Even more telling are quasars with abrupt redshift variations, their light spectra jagged like mountain ranges, as if photons traversed zones of space-time still trembling from a multiversal encounter. The implications rewrite our cosmic origin story. If redshift spikes stem from brane collisions, then Hubble's famous linear relationship between distance and redshift might not be universal. Instead, our cosmic map could be dotted with scars, regions where light tells two stories at once, one of expansion, another of a reality brushing against something stranger. Future telescopes like the European Space Agency's Euclid mission might hunt for these anomalies, scanning the sky for redshift patterns that curve unexpectedly, betraying contact with unseen dimensions. Yet the wildest possibility isn't just that we've misinterpreted redshift, it's that these collisions could be ongoing. Some models suggest our universe might be nested in a network of eternally colliding branes, each encounter birthing new cycles of creation. In this view, redshift isn't just a measurement, it's a cosmic seismograph recording tremors from realities beyond our own, each spike a whisper from a multiverse we're only beginning to imagine. Neutrinos might be the universe's most elusive particles, but what if they're hiding in plain sight, not as solitary ghosts but as a strange, ultra-dense fog? Picture a quantum sea so thick with neutrinos that light passing through it slows and reddens, like a car's headlights dimming in heavy mist. This isn't just speculative physics. Some theories suggest that in the universe's earliest moments, neutrinos could have formed exotic condensates, not quite solid, not quite liquid, but a bizarre quantum state where particles lose their individuality and behave as a single, icy entity. If remnants of these condensates linger today, they could be subtly stretching starlight across cosmic distances, tricking us into seeing expansion where none exists. The mechanics behind this are as chilling as they are elegant. In extreme conditions, like the unimaginable pressures just microseconds after the Big Bang, neutrinos, which normally ignore each other, might have been forced into proximity. Quantum effects could then bind them into a coherent condensate, a sort of neutrino, superfluid with properties unlike anything in our everyday experience. Light traversing this medium wouldn't just pass through, it would interact, its photons scattering off the condensate's collective neutrino field. Each interaction would steal a sliver of energy, stretching the light's wavelength imperceptibly. Over billions of light-years, these microshifts could compound into the redshifts we've chalked up to cosmic expansion. It's as if the universe has been breathing fog onto our cosmic lenses, blurring the true distances to distant galaxies. Evidence for this frozen neutrino sea remains indirect but tantalizing. The cosmic microwave background, the afterglow of the Big Bang, shows subtle temperature fluctuations that some models suggest could align with neutrino condensate distributions. Even more intriguing, certain high-energy neutrinos detected by observatories like IceCube arrive with energies slightly lower than expected, as if they'd leaked energy into an unseen medium during their journey. Could this medium be the ghostly residue of primordial condensates? Critics argue that for neutrino condensates to significantly impact redshift, they'd need to pervade the universe at densities challenging to reconcile with known particle physics. Yet proponents counter with a twist. If neutrinos have even a tiny mass, as recent experiments confirm, their gravitational pull could cluster them into vast, diffuse clouds around galaxies or cosmic filaments. Light skirting these neutrino halos might then redshift without any space-time stretching, like a whisper fading as it crosses a silent, frozen lake. The implications are profound. If neutrino condensates contribute to redshift, the universe's expansion rate might be slower than we think, or even static, with light's energy loss masquerading as motion. Dark energy's apparent acceleration could shrink to a phantom, a misinterpretation of light's struggle through this quantum fog. It's a reminder that the cosmos often speaks in riddles, and redshift, our trusted guide, might be carrying messages from a shadow realm of particles we're only beginning to fathom. What if photons aren't traveling alone? The standard model paints light's journey as a solitary affair, particles zipping through empty space, barely interacting with the quantum vacuum. But nature rarely settles for simplicity. Hidden in the gaps of our equations might be undiscovered particles acting as invisible companions to light, subtly shaping its path and energy across cosmic distances. Imagine a photon not as a lone wanderer, but as a hiker escorted by unseen guides, each step influenced by forces we've yet to name. Take the action, a hypothetical particle lighter than an electron, born from theories attempting to solve quantum puzzles. If actions exist, they could form clouds around galaxies, creating a kind of refractive medium for passing light. Photons entering these regions might oscillate into actions and back, like a traveler switching between invisible paths. Each transformation would siphon off a trace of energy, stretching the photon's wavelength over time. The kicker, this process wouldn't just redshift light, it'd polarize it in distinctive patterns, offering a fingerprint we could hunt for in quasar light. Already, telescopes like the Very Large Array are scanning for these telltale twists in distant radio sources. Then there's the dark photon, a shadowy counterpart to ordinary light that could mediate interactions between visible matter and dark sectors. Picture starlight crossing a region where dark photons briefly leak energy into hidden dimensions. The effect would be subtle, like a candle dimming behind frosted glass, but over billions of light years, it could accumulate into redshifts indistinguishable from cosmic expansion. Intriguingly, certain anomalies in particle colliders, unexpected energy, losses in electron-positron collisions hint that dark photons might already be flitting through our experiments undetected. But why stop at known candidates? Supersymmetry, a framework doubling the particle catalog, predicts Photons superpartners to photons that could mix with light in high-energy environments. If Photons exist, they'd act as cosmic dampers, scattering photons through extra dimensions and returning them to our universe slightly redder. String theory takes this further, suggesting entire families of modular particles that could dynamically alter light's properties based on the geometry of hidden spatial folds. The beauty of these ideas isn't just their audacity, it's their testability. Next-generation telescopes like the Rubin Observatory will map millions of galaxy redshifts with unprecedented precision, hunting for deviations from Hubble's law that could betray light's secret interactions. Meanwhile, underground labs are refining action detectors using ultra-cooled magnets, and particle colliders are probing energy regimes where dark photons might materialize. Critics argue that inventing new particles risks becoming a fix-all for unsolved puzzles. Yet history favors the bold neutrinos, and antimatter were once mere scribbles in theorists' notebooks. Whether these hidden mediators ultimately explain redshift or not, their pursuit reveals a deeper truth. The universe's greatest mysteries often hide in the spaces between our equations, waiting for the right lens to bring them into focus. Every anomalous photon could be a postcard from a frontier we're only beginning to imagine. The cosmic microwave background isn't the only ancient globe bathing the universe. There's another, far more elusive relic humming just beneath our detection. Moments after the Big Bang, the cosmos wasn't just a soup of light and plasma. It was flooded with neutrinos, trillions of these ghostly particles streaming through every square centimeter of space. As the universe expanded and cooled, these neutrinos decoupled from matter, forming a cosmic neutrino background that still permeates everything today. Unlike the CMB's sharp microwave snapshots, this neutrino fog is nearly impossible to detect directly, but its gravitational whisper might be hiding in the redshift of distant starlight. Picture a galaxy's light traveling billions of years to reach us. Along its journey, it doesn't just pass through empty space, it slices through this sea of primordial neutrinos, their combined gravity subtly bending space-time like a ship's wake disturbing still water. Each neutrino's tug is vanishingly weak, but across cosmic distances, their collective influence could stretch photons just enough to mimic part of the redshift we attribute to expansion. It's as if the universe has been quietly adding weight to light's footsteps, making distant galaxies appear to recede faster than they truly are. The math behind this is both delicate and profound. Neutrinos, despite their minuscule mass, outnumber atoms in the universe by a factor of 1 billion. Simulations show that if even a fraction of them clumped around cosmic filaments, those vast, web-like structures connecting galaxies, their gravitational lensing could skew redshift measurements by measurable fractions. Some models suggest this effect might explain anomalies in supernova brightness, where certain distant stellar explosions appear oddly dim compared to expectations. Instead of dark energy accelerating the universe, we might be seeing light fatigued by neutrino fog. Hunting this signal is like trying to hear a whisper in a hurricane. Traditional neutrino detectors, like Japan's Super Kamiokande, are built to catch high-energy neutrinos from stars or particle collisions, not the ultra-low-energy relics of the Big Bang. Yet next-generation experiments are rising to the challenge. Projects like Ptolemy aim to trap these ancient neutrinos using ultra-cold graphene sheets, while cosmological surveys scour redshift data for patterns that betray the neutrino background's gravitational fingerprint. Even the cosmic microwave background might hold clues. Its polarization patterns could carry imprints of early neutrino density fluctuations, like shadows cast by invisible giants. The implications ripple beyond redshift. If the cosmic neutrino background contributes significantly to light's stretch, it could recalibrate our cosmic expansion rates, easing tensions between conflicting measurements of the Hubble constant. Dark energy's dominion might shrink, replaced by the subtle mechanics of particles we've long overlooked. But the real revelation is humbler. The universe doesn't just speak to us through light. Its oldest messages are carried by ghosts, and if we learn to listen, they might rewrite the story we thought we knew. From tired light to vibrating brains, we've toured 36 extraordinary explanations for cosmic redshift, each one a doorway to a radically different universe. Some ideas feel like relics from cosmology's attic, dusted off and given new life by modern math. Others stretch the imagination so far, they blur the line between physics and philosophy. Yet all of them share a rebellious spark, the refusal to accept that redshift story has been fully told. Think about what this means for how we see the cosmos. For nearly a century, Redshift has been our compass, guiding us to map an expanding universe dotted with dark matter and propelled by dark energy. But peel back the layers and suddenly that compass starts spinning. Could redshift be light's fatigue after crossing quantum foam, a side effect of hidden dimensions, or even a cosmic illusion crafted by primordial black holes? Each alternative reshuffles the deck of modern cosmology, offering new ways to interpret the night sky's deepest signals. Here's the thrilling part. We don't need to discard the expanding universe to embrace these possibilities. Science thrives when competing ideas collide, refining each other under the pressure of observation. Maybe the truth lies in a hybrid model, expansion plus something stranger, like a universe where dark energy shares the stage with variable constants or neutrino condensates. Or perhaps one of these fringe theories will someday topple the mainstream, just as Einstein's relativity upended Newton's clockwork cosmos. What ties these threads together isn't just curiosity, it's humility. Every time we measure a galaxy's redshift, we're decoding a message that's traveled billions of years to reach us. To assume we've perfectly translated that message, with no room for surprises, would be like ancient astronomers insisting the stars were mere holes in a celestial tent. The universe has a habit of outsmarting our neatest theories, revealing layers of complexity we never anticipated. So where does that leave us, not at an endpoint but at a crossroads? The next generation of telescopes, from the Vera Rubin observatories all sky surveys to the gravitational wave detectors listening for spacetime's ripples, will test these ideas with unprecedented precision. Some theories will crumble under scrutiny, others might reveal cracks in our standard model, pointing toward physics beyond Einstein, beyond quantum mechanics, beyond anything we've yet imagined. That's the beauty of cosmology. It's not just about finding answers, it's about learning which questions we've been too myopic to ask. So keep looking up, keep questioning, and above all, stay comfortable with the unknown. The universe's greatest revelations often begin as heresies whispered at the edges of science. Who knows, the next revolutionary idea might be hiding in plain sight, tucked between the lines of a redshift measurement, or in the comment you're about to leave below. The cosmos is listening. If this cosmic journey through the wild frontiers of redshift has left your mind buzzing with possibilities, you're not alone. Every like, subscribe, and notification bell tap fuels our mission to keep tearing apart the universe's playbook, because the best discoveries happen when we dare to question what's written in the stars. Imagine getting alerted the moment we drop our next investigation, whether it's dissecting black holes that defy physics or decoding signals that might rewrite Einstein's rules. This isn't just a channel, it's a launch pad for collective curiosity, where your engagement turns into rocket fuel for deeper dives. Hit that subscribe button now, because the cosmos never stops surprising us, and neither should we. Let's keep unraveling mysteries together, one mind-bending revelation at a